Okay, thank you everyone. For our last speaker of this session, we have Bobak Kiani, who's going to tell us about slow mixing of quantum Gibbs samplers. Thanks.
Thank you for the introduction, and thank you all for being here. The work here I'm going to talk about is joint with Alexander and David. I think Alexander is here today in the back, yeah. So if you have harder questions, you can bug him. Our motivation is basically we want to understand what is a bottleneck in the quantum setting. So bottlenecks are things that make optimization hard. Local minima. In largest clique, you have, for example, if you start from one clique, you have to go to another that may be larger. Local changes may get you stuck. The intuition we want in this talk is to say, what is the quantum analogs of these that makes things hard? And the particular thing we look at is Hamiltonians, quantum systems that interact with some Bath, with some nature. The previous talks have also been on this, so hopefully I can go through the introduction fast. And the goal is, given some quantum system, which is described by Hamiltonian, we wanted to have a quantum computer that's able to sample from this. So this quantum computer should be able to give you states of this system. This is an analog of a classical problem, which here we have states which are, for our purposes, bit strings. And the energy will be just a function, gives real numbers. And we have a beta, which is our inverse temperature. And we want to sample from the energies, the states corresponding proportionally to their energies. And on the quantum side, which similar to the previous talks, here we have some thermal state, which is now a PSD matrix. H is now a Hermitian matrix, which when we take its exponential, constructs a distribution over eigenstates of H. And again, these eigenstates are sampled proportional to e to the minus beta of the energy of the eigenstate. And for what I'll do for this talk, I will say we have a Gibbs sampler whenever we have some quantum channel which maps states to states. And the fixed point of this quantum channel is the thermal or Gibbs state. And equivalently, if we have a Lindbladian, which is just a continuous time version of a channel, we will also say its fixed point will be the Gibbs state. And there are many different channels and Lindbladians which have the nice property that if you run these channels or Lindbladians for infinite time, they will converge to the Gibbs state. The canonical example of this is the Davies generator, which models nature, but it's hard to simulate on a quantum computer because of time energy uncertainty principles and the need to distinguish eigenvectors. But more recently, in a series of breakthrough works, people have come up with efficient samplers that also have the nice property that they're able to converge to the Gibbs state in infinite time. And these constructions are approximations of the Davies generators or other systems that are stuff we can actually perform on our quantum computers efficiently. But yeah, so in infinite time, these things will create the Gibbs state. But naturally, you might ask, like, we don't have infinite time, so how long does it actually take in practice to get close to it? And the natural measure people use to study this is what's called the mixing time. And this is here formally defined as the minimum time t, such that for any initial state, sigma, if we apply the Lindbladian or sampler for time t, we'll contract a quarter amount from the trace norm towards the Gibbs state. This is just one definition. There are other various definitions of this in the literature that change up to constant factors, but we'll just use this one. Some remarks. Here is the Schatten norm or the trace norm. So just the sum of the singular values. We'll use this as our measure of progress. And here we'll measure, you should see it as the time to get a constant factor approximation to the Gibbs state. So this is the time it takes to roughly reduce your error by a quarter. And this is also a worst case statement over initial states. So if you want to prove slow mixing, you would say there exists a state for which the time takes this long to produce this outcome. And the general picture we'll come to see in this talk is that for many Hamiltonians, this is illustrative, but for many Hamiltonians, there'll be some critical temperature below which some critical beta below which the mixing is fast. And by fast, I mean polynomial in n in the system size. And above that, it'll be slow. I don't mean this as an exact statement. There might be slow transitions or whatever, but the picture you should have in your mind is that there will be some beta large enough for which there will be slow mixing. And we show slow mixing from what we call quantum bottlenecks, which will be the focus of the rest of our talk. And I also want to highlight a recent work by Raskovsky et al., where they have similar bottleneck findings from a more physics point of view. Before we jump into the math, why do we care? Just a few reasons. Sometimes when we show slow mixing, we learn some physics about the problem, some properties, topological, geometric, so on. We want to know the limitations of our Gibbs sampling algorithms that have become very hot in recent years. And also sometimes we want to engineer slowness into a system. So if you've heard of self-correcting memories or error correction, you often want to prepare a state that is protected from nature, which you can treat as a Gibbs sampler. Okay, so jumping to the main result, we give a quantum bottleneck condition that gives sufficient conditions to show exponentially slow mixing. And here by exponentially slow mixing, I mean it's exponential in the number of qubits, or the number of degrees of freedom. And we will apply this to various different examples. So for example, classically hard Hamiltonians for which people have shown in the classical literature that they mix slowly. We can also show mix slowly for these quantum samplers. We'll show that quantum LDPC code Hamiltonians, those with good distance, will also mix slowly. And finally, I like this last one a lot, which is the transverse field Ising model. It's a non-commuting model, which we can show mixes slowly. Okay, so the rest of my talk will get a bit more technical, but I'll try to go slowly. I want to first give some intuition for how the bottleneck arguments work. Then I want to highlight the two main things you need to show a Hamiltonian mixes slowly. The first is that there is a bottleneck region of low probability. And the second, which is, I think, unique or more unique to the quantum setting, is you have to show samplers can't traverse the bottleneck in one step. And finally, I'll discuss some implications. Okay, so intuitively, a bottleneck is a high energy region that you have to pass through to sample from the other side. Since we are doing a sampling problem, you have to be able to sample IID, which means both sides have to be treated equally. And if you get stuck in one side and you can't traverse through to the other side, your sampler will be slow. And we need to show two things for this to work. The first is that this bottleneck does exist. It's a region of low probability. And the second is that to get to the other side of the bottleneck, you have to apply multiple steps. We can't just jump through it. In the quantum world, how does this work? One way to do it is we split the set of states into three subspaces, each with an orthogonal projector. I'll call these subspaces pi A, pi B, and pi C. Pi B will be the bottleneck region, and pi A and C will be the regions on both sides of this bottleneck. And our bottleneck dilemma works like this. If you're given a Gibbs sampler and these three different projectors, if you have proven the first thing, that this bottleneck region has small probability, that if your state is in A, you can't jump to C with one step of your sampler. I've equivalently written it here in the adjoint of the sampler form. So the sampler here, its adjoint is dominated by pi A plus pi B when it's applied to pi A. And then we have a final technical condition, which is an initialization condition, which often holds trivially. I will just skip this. It just basically says at initialization, regions are decoupled. If you have these three things, then you will have slow mixing. And oftentimes, the devil is in proving the first two conditions. So I'll give some examples and go through those in detail. So as I go through the rest of the talk, I'll try to discuss each of these two items here and how this can be done. And I will say before I go through this, proving these things can be very hard in general. So especially the first condition, proving some region has low probability, can be a very challenging task, especially for non-commuting models. And the examples we give are those for which we can prove it. Okay, so the first thing you have to show is that bottleneck regions have small probability. This basically means that the ratios between the probability of being in A and the probability of being in B, and also the ratio of being in C versus being in B when you sample from the Gibbs state, these ratios are exponentially large. So if you sample from the Gibbs states, you're much, much more likely to be in A than you are to be in the bottleneck, and similarly for C. Showing this depends on the Hamiltonian properties. The topology of the Hamiltonian, overlap gap property, if you've heard of that lingo, expansion properties of graphs, and so on. I'll give some examples later. The second thing you have to show is that a single step of the algorithm cannot pass through the bottleneck. This is a kind of more, I think, unique to quantum thing, so I'll go slowly through this. We discussed two ways to do this. One is to show that your Gibbs sampler is a local sampler, local here in the Pauli sense, meaning if you were to write this sampler out, it is low degree in the Pauli operators. And this works well for lattice models. The second way we do this is through the jump operator distance. And this is something that I'll describe in a little bit. But just keep in mind that there's two options here, and we discuss both in the paper. I think the first is a simpler one to describe. A sampler is a local channel if it acts as non-identity in a small region of R qubits. This is often done via Lieb-Robinson bounds. It's a more standard technique, I think, in the quantum community here. And this works for lattice models. These Gibbs samplers are quasi-local when you have a Hamiltonian that's a lattice, and you can use existing Lieb-Robinson bounds to prove that these samplers cannot jump between different regions. But what if you're not on a lattice? Things get a little bit trickier. So we describe this jump operator distance for this setting, which is also shown in some prior literature too. But I just want to go slow through this so we understand what's going on. So let's first look at classical settings. In MCMC, which previous people also described, here we transition between states to sample. So we start at some state x naught, and iteratively we change bits one at a time to create a sample. An example in Metropolis Hastings, it's a very simple algorithm. You pick a bit at random each step. You flip that bit, get a candidate state, and you accept that state with probability proportional to the ratio of the candidate state versus your current state. So each step, you're only flipping one bit. That's the key point I want to make in this example. And in the quantum case, we describe this whole business through jump operators. But here in the classical side, we have all these Pauli x's would be the jump operators. To go from state t to t plus 1, we pick one of those jump operators. And then we have a set of transitions. In the classical case, is just all the bit strings that differ in just one bit. And the key point here is that the sampler is a weighted sum of these transitions. Now, it may be hard to write this in practice, but you can imagine that if you were to write down the whole sampler as one big equation, it would just be a weighted sum of these samplers, of these transitions. The quantum case is similar. Here we have jump operators, which are often treated as the single qubit Paulis. And the Hamiltonian has an eigenbasis, which I'll just list as ket I here. And the set of transitions now are the ones where we can go from some eigenstate I to j through one of these single qubit Paulis. And these are like the neighboring eigenstates, analogous to the classical setting. And if you work out the quantum samplers, I don't have the proof here, but you can come ask me for details later. If you look at a lot of these quantum samplers, they are low degree in these transitions. They won't be linear in these transitions. A lot of them are quadratic, but if you write out the equations, you'll see that you can write them as a weighted combination of two of these different transitions. So this gives you another notion of distance. Two eigenstates will be far apart if you have to do many, many transitions to get from one to the other. And this notion of distance works really well when you have an eigenbasis. So For models which are commuting, where we know the eigenbasis, or perturbed models, where we know the eigenbasis before the perturbation, you can use this notion of distance to prove the second part of the slow mixing lemma. Okay, so I'll just go through the examples we were able to show slow mixing for. The first are classical Hamiltonians. There's a whole literature now on Hamiltonians that are classical that are slow mixing. It's easy to see using this transition definition, the jump operator distance, that the quantum Hamiltonians will also be slow mixing for these Hamiltonians too. These classical bottlenecks will also obstruct the quantum Gibbs samplers. The LDPC code Hamiltonians are another one. Here we use the distance properties of the code to show that you have to do a lot of sampling steps to go from near ground states, near code states. Our subspaces A and C will be two orthogonal near code states. And finally, we do the transverse field Ising model. Here, this is a stochastic model. Stochastic meaning that it's a semi-quantum model where it's possible to evaluate probabilities. The way this works is it's a perturbed 2D model. The classical side is just a purely Z-basis Hamiltonian. It's on a 2D Ising model. And you add sum of xi's to it. So you add just transverse field x terms. This makes the model non-commuting, but there are still nice ways to calculate probabilities in this model using this Feynman-Kac formula, which lets you evaluate these stochastic Hamiltonians. A lot of the work in our paper was actually to evaluate this whole system here for the transverse field 2D Ising model. And this model, we also use the first notion of distance, which was the locality distance, the fact that you can use Lieb-Robinson bounds when Hamiltonians are defined on a lattice. Okay, looking ahead, a couple questions that we are really excited about. One issue people bring up with mixing times is that you're allowed to pick an initial state. It's worst case over initial states. So here when we say it's slow mixing, we say there exists a state for which the Gibbs sampler takes a long time to mix. You might naturally ask, what about a typical initial state, like the identity, for example? It turns out this is hard to analyze even classically, but there are works coming out that are trying to do this, and if people have ideas, we'd love to chat. I think a bigger question, going back to my first slide, does this bottleneck argument work beyond just sampling algorithms? Is this a property of quantum systems that is endemic to hardness in general for quantum systems? And it'd be nice to take a lot of the ideas here to show slow mixing, to also say other algorithms as well will struggle. So thank you guys for listening to me, and I appreciate it.
Thanks for the talk.
Yeah.
Do you have any algorithms in mind that might be obstructed by slow mixing?
Oh, yeah, I mean, QAA, for example. I don't know, phase estimation. Yeah, I don't know. There's tons of ones. Classically, there's, I think, a really nice set of literature coming out now that like disproves stable algorithms, low degree algorithms, and so on. And a lot of these proofs require us to define what it means to have OGPs or bottlenecks and so on. And I think the quantum side is comparatively much less studied. And it's a lot of nice ideas there, yeah.
Hi, great
Oh,
talk.
Hi, thanks.
I meant to ask how essential the detailed balance condition is in your proof technique, because there are some, like Lambdadians associated to non-commuting Hamiltonians, which only have the Gibbs state as an approximate fixed point.
You said detailed balance?
Yeah, you assume like the Gibbs state is fixed under the dynamics. You could imagine the Gibbs state is only like approximately fixed.
Yeah. You can probably get more. I'm not sure. We didn't assume any detailed balance condition here, just that it's a fixed state and it's local in this sense. I think you can probably get better proofs if something like that is assumed, but I'd need to know the details, and I'd love to chat about it. Yeah.
Yeah, maybe I have a very similar question. So maybe following up, like
Yeah.
in your proof, like you talked about, it is like somehow the transition rate is given by a thermal state and the vector. I guess the question is, if you have a generic Lindbladian, like kind of trying to make analogy with even classical Markov chain in general, like
Yeah.
yeah, maybe as a clarification, so your algorithm doesn't really, sorry, your result doesn't really make any assumption about whether or not it satisfies it is simulating like a thermalizing process.
The only requirement we make on the Lindbladian is that its fixed point is the Gibbs state. So if you apply the Lindbladian to the Gibbs state, it keeps it invariant. It doesn't change it. And this, you also have to show this Lindbladian is local in the sense that you had the two options I showed earlier, where you had the jump operator distance or the locality. Did I maybe understand your question there?
Yeah, sorry, that also wasn't clear. Like, for example, does that assume you have a unique steady state, or like what happens if you?
No unique steady states needed for this, no. Yeah.
Thanks for the talk.
Yeah.
Maybe I missed something, but do you have any intuition on what exactly the slow mode is for the transverse field Ising model? Because it seems like if the transverse field is strong enough, then it's also easy to classically sample it. So
Yeah. So I don't have a slide on this, but the slow modes, the transverse field Ising model will be, the bottlenecks will be fault lines. So the initial state will be something which has all pluses, for example, close to all pluses, and to traverse through it, you need to go through a fault line. A fault line being like you have to flip a whole row of things to move from one side to the other. This has an energy gap that's like square root n if you have the whole thing is n by n. Sorry, it'll be n if it's n by n. And our result only works for small enough, but still constant transverse field strength.
oh, so it only works for small enough transverse fields.
Yeah, because
I
if it's
see.
strong enough, then you can
Yeah,
just,
I see,
it
I
should
see.
be a product
Right,
state.
right.
Like
Okay.
it'll just be, yeah, it'll be a single qubit thing. So
Does it work all the way up to the quantum critical point, for example, or the phase transition point? Or is it like, can you only prove it for perturbatively small v?
it's a constantly small, I think, I'm not 100% sure about that. I think Alexander would maybe know, but I think the value that occurs for that is around 3 point something, and we get up to like 1.
Oh,
So there may be a gap, but again, Alexander might know more. He spearheaded that part.
thank you.
Yeah.
Thanks for the talk. So I think in the beginning you mentioned that one motivation of this slow mixing actually related to this, I think, self-correcting quantum memory or something.
Yeah.
I wonder from your construction, is that possible to get a quantum memory for any system that satisfy your condition? Or, I mean, is it clear how to go from, this slowness go to a quantum memory?
Yeah. I think you would need more in a self-correcting memory. Like you would want it to be a ground state. The thing that's protected has nice code properties and so on. Here we would just show that here's a technique, I guess, to take a initial state and show that it mixes slow. So self-correcting memories probably have more than just that. But yeah, I think you can use these techniques to do stuff like that.
Thanks.
Yeah.
One thing I'm wondering is in your proof, do you need the jump operator in your Lindbladian to be rigorously local, or it can be quasi-local?
The jump operators themselves?
Yes, the jump operators themselves. Because in most of the previous algorithm, and although the coupling operator is local, the jump operator is actually quasi-local. Yeah, so
the jump operator is quasi-local.
Yeah.
So the jump operators, when we were defining them, or maybe you can explain to me, we assume them to be single qubit polys or order 1 degree polys. You can maybe expand that to like growing if your gap between states is like larger. So if you have states that are like separated by Hamming distance order n, then you can let the jump operators grow in locality. But I have a hunch you were referencing something else and I maybe misunderstood you.
Oh, I see. So, so maybe we can discuss this later. Thank you.
Okay. Okay. Yeah, sure.